For chapter 5, day 4, we're really just going to do a lot of practice. You guys have done all of this stuff in the past. I'm going to show you something a little bit new on the back with your calculator, but most of this is going to be practice. We'll have you do some examples on your own, and then we'll get you guys going on to your homework. So talking through numbers 1 and 2, we'll take a look at number 1 real quick. This is an exponential function, and it's just saying that the function f of x equals 2 to the x and g of x equals blank are inverse functions. Well, let's say hypothetically we didn't know what that was already. We can find the inverse right away by switching x and y. So if we switch x and y, and then the way we get y by itself, remember we use logs. So y equals log base of the log matches the base of the exponent. And there's our inverse. We got y by itself. That goes back and replaces with our function notation. But as we already knew the property, because our exponential and log functions are inverses of each other, we can use that and say that f of x equals 2 to the x and g of x equals log base 2 of x are inverse functions. For number 2, we're looking back at an old property. It's a polynomial. It says let f of x be that polynomial. Given that this exists and 4 is in the domain, we want to evaluate f of f inverse of 4. Well, we know because the inverse exists and we're taking the composition of its inverse and 4 is in the domain, we can just use the fundamental inverse property, inverse function identity, which tells us f of f inverse of x is just equal to x. Again, as long as x is in that domain. So we can just say that this answer is 4. Just a little quick review about that property. For number 3, this is more practice on what we did yesterday. It's just evaluating your log functions. So if we take a look at the first one, we want to evaluate what this actually is without a calculator. The way we do that is we'll set this equal to some unknown. We'll call it x. And then we have to convert to exponential in order to do that. So we take the base of the log. That's going to be the base of our exponent. Make that other side the exponent. And then the inside of the log is going to be the answer. Now that we have this set up, we can go ahead and change the base so that the bases match. Luckily for us, we know that 25 squared is 625. And since it's in the denominator, we can make it a negative. Now that the bases match, we can set the exponents equal. And the nice thing about this is it's already got x by itself. So this is stating that the log base 25 of 1 over 625 is equal to 2. If we take a look at part B, the second one, go through the same process. 16 to the x equals 1 over 64. This one's a little bit more tricky just because the common base isn't only changing one side. We actually have to change both sides. Remember that x is over there, so we have 4 to the 2x, 4 squared is 16, and then 64 is 4 cubed, but again, because it's in the denominator, make it a negative. And again, now that the bases match, we can set the exponents equal, but in this problem, we got one extra step, so x equals negative 3/2, which again means that log base 16 of 1 over 64 is negative 3/2. If we take a look at the third one, same process, except what we notice here is bases match. We get x equals 1. So this is telling us that log base 10 of 10 equals 1, which we're going to talk more tomorrow about our logarithmic properties. There's other properties involved, but we'll just show you this property real quick since we're showing it right here. If the base of your log matches the base inside the log, they essentially cancel and you're left with just 1. That is a property that we're going to show again tomorrow, but now you know it a day before. So go ahead and take a minute real quick. Try doing this fourth one on your own. And then when you're done trying it, unpause the video and check your answer to make sure you got it right. So if we take a look at this fourth one real quick again, we set it equal to x. When you convert, we have 2 to the x equals the entire inside of that log. And then we got to go through a little bit of exponential properties here, changing all 3 bases. And then because the bases on the right match, you would add these 2 exponents, and that's how we got the 7/2, in case you were wondering about that. And then you can set the exponents equal. If we take a look at number 4, we're going back to graphing, kind of like we did yesterday. It says graph the function f of y equals natural log of x. Yesterday we graphed just log functions. If we used our calculator, we could go ahead and just type this in. We get a basic table there. Again, we notice that natural log of 0 is undefined, and then we get some decimal outputs, and this is what our general graph looks like. So if you notice, it looks very similar to the log graph. It's just a little bit flatter, a little bit more turned. It has a sharper turn. But we're going to treat it the same way. When we graph these, we're going to use this natural log of x as our base function, and then we can apply transformations to graph any other natural log graph, just like we did yesterday with log graphs. So if we did this one, we already have the graph. The domain is from this asymptote at x equals 0. So we can put that vertical asymptote there at x equals 0. The domain is from that asymptote to infinity. The range, even though it does level off quite a bit, it technically is still going up forever, so it would be negative infinity to infinity. And then the x-intercept, we can see it on that graph there, would be 1, 0. So that's the base function for natural log of x. For number 4, oh man, we got 2 number 4s. So next one, we'll call it 4b. We're going to graph y equals natural log of negative x plus e. So using that base function, we can graph 1, 2, 3, 4. We can graph a general sketch of what the base function looks like. So again, this is just natural log of x. And what we want to do here, change the color, is this negative on the inside. The negative being multiplied on the inside means we're reflecting over the y-axis. So it's going to be a horizontal reflection. So that's the first thing we can do. So we can flip it, reflect it over that y-axis. So that's the first transformation. Didn't affect our vertical asymptote. And then the second transformation, plus e, is going to be up e units, which again, remember, is approximately 2.71. So I'm going to take each coordinate here and go up 1, 2.71. And again, for these, since we're graphing by transformation, just do the best you can. It's not going to be a precise graph because we're dealing with some interesting numbers, but get it as close to possible, as close to it as you possibly can. And that green one is our final graph. So using that graph, the domain, this time we're coming from the left up to 0. So negative infinity up to 0. The range is still up and down forever. We're going to come back to the intercept. The asymptote did not change. But let's go ahead and talk about the intercept. So the intercept, in this case, it looks very close to 0, but we can't tell. So just like we can do any other time, if I want to find an intercept, we can tell there's no y-intercept because we have that vertical asymptote on the y-axis. But there is an x-intercept. We can see it going through that x-axis. So how do we find an x-intercept? We set y equal to 0. So let's go ahead and go through some algebra here to find it. Subtract e. So negative e equals natural log of negative x. And then since x is on the inside, we got to convert. to exponential form. So remember the base is e. So we have e to the negative e equals the inside of our log function, and then just divide by a negative. So we have negative e to the negative e equals x. And I know it looks goofy. If you want, because there's a negative in the exponent, you can say x equals negative 1 over e to the e. And it looks like a goofy number. Just remember e is a decimal. It's just like any other number, so we can write negative 1 over e to the e, comma 0. And that's our x-intercept. It's the only intercept we have on this graph. Okay, so that's the graphing. If you take a look on the back, we look up top. It says simplify the following. If you want, you can pause the video and try these ones on your own. It's going to be very similar to the ones that we did on the front, those 3 evaluating the expressions. For these ones, we're just simplifying, but otherwise we're just going to kind of go through these. So if we take a look at this, we're going to do the same thing we did on the front. E to the x equals e to the 1. Well, we already know, because that natural log has a base e, we already talked about this property, x is going to be 1. So remember, if the base of the log matches the base of the inside, then they're going to cancel. So if we take a look at the second one, same concept. E to the x equals e to the negative 2. Bases match. X equals negative 2. This is actually going to bring us to another property that we're, again, going to see tomorrow. If the base, we use log, if the base of the log matches the base of the inside, but in this case, if there's something else in that exponent up there, these will cancel, and you're left with that exponent. So that's another property. We'll see it tomorrow. We'll go through it again tomorrow. But again, since we're seeing it now, might as well use it. Now, here's the trick, though. If we take a look at this next one, this is not, you cannot use that property. Okay? What we can do, though, is we can look at the inside, and we can evaluate the inside first by saying natural log of e, which we already said over here, natural log of e was 1. So we can say natural log of e equals 1, and then we can replace that back in there and say 1 to the negative 2. Well, that's 1 over 1 squared, which is just 1. Okay. One thing, again, that you cannot do, you cannot use that property that we just talked about on the last one, because if you do use that property and you just say, oh, these bases cancel because they're the same, you end up with negative 2. Notice these are not the same answer. Okay? The reason this property doesn't work is because this exponent in this case, as you can see, is not the exponent of the inside of that log, it's the exponent of the entire thing. Okay? So you got to be really careful about that. Make sure you're applying the correct properties and following with the correct exponential rules. If you take a look at number 6 and 7 and 8, if we look through this, it's saying that we want to use a graphing calculator to estimate the roots to the nearest 1/10, then solve the equation algebraically by first rewriting it into logarithmic form, and then see that the answers are consistent. So if we look at this one, I'll show you both ways for this one. It's tough to see here, but just be aware. This is 10 to the second, and then the second is being raised to the x minus 1. So if we go through this one on the calculator, what we would do is, because these two are equal, we're going to set y1 as our first equation, which is on the left side, and the y2 as the right side. Now I'm going to go ahead and show you on the calculator exactly how you type these in, and then the steps that you go through to find that answer. When you go to type these into your calculator, you go to the top left, hit y equals. Again, there are y1 and y2. Always just be careful when you're typing them in, make sure they're correct. Then you're going to hit graph. Most of you are probably going to have your window at a 10 by 10. So if you look at your calculator, you're probably going to look like this. But again, as we talked about, our y2, still loading, our y2 is 145. So that's just a horizontal line at 145 units up. So if we look at our window, you got to go to your window here. We need our y max to be at least 145. So I'll make this one, we'll say 160. I'll make this go up by 20 just to make it look nice. So now that's stretched out my window up by 160 units so that I can see, in a minute, you can see that line come through. And now the spot we're looking for is that intersection, okay? The way you find the intersection is second trace or calculate. We want to look for the intersect and then move the curve, the dot on the curve, enter, and then it should be on the other curve, enter, and then enter a third time for guess, and it'll tell you that intersection point. So for this problem, the intersection is at 2.1, 145. Now that we found that intersection, we can say that the x value for that intersection, because we're solving for x, it says round to 1/10, is approximately 2.1. So the calculator is telling us the estimation is x equals approximately 2.1. Now we're going to solve it algebraically to make sure that the algebra holds up. So if I do the algebraic approach to solving it, we have our equation. First thing we want to do is I got two exponents. I got an exponent and then a raised to another exponent. Is remember your power to power rules states that these two can be multiplied. So I'm just going to say this is 10 squared to the x minus 1. This is the same thing because that would be as if those were exponents of each other. So I have 100 to the x minus 1. This is just going to make it a lot easier because now when I convert, I have log base 100 of 145 equals x minus 1. Then we can go ahead and add the 1 over. X equals log base 100 of 145 plus 1, leave it on the outside, and then that's equal to our x value. So all we have to do now is type it in. Remember log base b of a. If you got to type these in your calculator, you don't have a button on your calculator that is log base. So we can type this in as log of A over log of B. Log of B. So when we type this in, x equals log of 145 over log of 100 plus 1, and that's approximately 2.1. It's a little bit off, but again, that's because we solved algebraically and we didn't round like the calculator did until the very end. So go ahead and try these last two problems, the 7 and 8. Pause the video and then give them a shot. And then when you're done trying them, unpause it and we'll walk through both of them. At number 7, the calculator should have given you 0.8. And then algebraically, when you go through this, first thing you got to do before you can convert to log is you got to get rid of this squared. So when you square root it, you have 10 to the x equals plus or minus square root of 40. But then again, you got to convert it to get the variable out of the exponent. And then we highlighted this here. We made a little note. We have log base 10 of plus or minus the square root of 40. The inside of a log cannot be negative. So that gets rid of that negative root 40. But we do see that the log of square root of 40 is approximately 0.8. So it shows that our calculator one matched. If we take a look at number 8, same thing. Calculator this time has two intersections, a negative and a positive. A negative answer is not always unacceptable. You have to follow the rules. Negative can't be inside the log, but you can have a negative answer. In this case, our original equation is an exponential. So when we go through to solve it algebraically, first thing we want to do is convert it, and that's what we did here. Remember, the base of the log matches the base of the exponent. So we had natural log of 112 equals 3x squared. And then we divided by 3. So that had x squared equals natural log of 112 over 3, square root. And then again, when you square root, it is plus or minus, because in this case, that minus is allowed because it doesn't make the inside of the log negative. And then when you type those in, you get approximately 1.3. So that's just a few of the practice problems you might see on your homework tonight. Go ahead and try that homework. And if you guys have any questions, again, please feel free to reach out to your teacher and ask them for any help. Good luck.